ready right now? Okay.
All right, thank you. Please go ahead.
Okay. Thank you for introduction, first of all, and happy Monday, everyone. So again, I'm Mingu Kang in UC San Diego, and also assistant professor and the principal investigator of the vertically integrated VLSI processing lab, VVIP lab. Our group is focusing on the low power, high performance VLSI implementation of AI, or sometimes just traditional signal processing algorithms. So while we are mainly focusing on the algorithm and hardware co-optimizations, we also emphasize some silicon prototypes to deliver more reliable and also trustworthy academic findings. So again, this work, the hybrid RRAM-based PIM for transformer, this is collaborated work with Professor Namsun Kim in UIUC and Tana Rosin in the CSE department of the UC San Diego. And my first author, Chang'un Song, is right now in this call. So maybe if you have any question, maybe he might be the best person if you want to seek implementation detail. Okay. So you might be sick and tired of seeing this kind of the figure right now, right? So LLM models are increasingly used across many applications, and also generative AI models continue to scale rapidly, so as illustrated. And also the computational overhead shown on the y-axis becomes a major challenge. So at the same time, rapidly increasing the data volume worsens the memory wall problem, limiting the system performance, especially rather than summarization, the generation case, the memory wall problem is intensified. So as a solution, so von Neumann's architecture. So to address the issue of the von Neumann's architecture, processing in memory architecture has been introduced earlier and also highlighted a lot. So in the conventional von Neumann structure, we need to consistently shuttle between processor and memory, causing some memory wall issue. Here there is a memory wall issue. On the other hand, PIM case, the computing is deeply embedded inside the memory or sometimes near the memory bank. So dramatically reducing the volume of the data movement as shown here, and also so that minimizing the latency and also energy for the data transfer. So before I jump on the detail, let me briefly provide the necessary background regarding non-volatile memory-based PIM operation. So here I'm going to use based on RERAM, resistive RAM, but it doesn't necessarily need to be RERAM. It can be PCM or SOM or any type of the NOR structured memory is applicable. However, RERAM might be good candidate given multi-level cell, the favorability and also the fast or read operation. So generally, I'm going to talk about GEM-V operation, like a general, general matrix and vector multiplication case. So as shown here in the analog PIM operation, the input weight is broadcasted as a voltage level. First component, second element, third element as a form of the voltage. On the other hand, weight will be stationed inside the array memory as a conductance. What is a conductance? Conductance is nothing but 1 over R. So V divided by R is nothing but current. So each individual cell will generate the current which corresponds to the multiplication. And then all of the rows are performing the same operation so that the current will be summed up, generating this sum operation. So this is exactly following the dot product operation. So as you can see, all of the rows are parallel, and also all of the columns are also parallel. And then at the output, we will generate the dot product result. So this is extremely parallel operation. And also it is analog operation, so ultra low power and also high density. Now let us move forward the digital PIM operation. I would not go too much detail, but high-level principle is two input operands and then binary operation. Based on NOR operation, we can program the output. And then what if only NOR can actually build based on NOR or NAND, you can build any type of the arbitrary function. So by modulating this phenomenon, you can program all of the rows in parallel. So this is a digital PIM operation. So the writing is because this is a digital operation, you do not need the analog to digital converter, first of all, and also higher accuracy can be achieved. However, it is not really all parallel in terms of the column and row. So in that sense, the parallelism might be slightly limited compared to this analog PIM case. So to summarize, efficiency-wise, analog is better. Accuracy-wise, the digital PIM might be much better. But digital PIM is based on single. Okay. Anyway, I need to comment one more thing. So another background in the non-volatile memory. Single level cell store either 0 or 1. This is the single level cell. So naturally, noise margin is pretty far, so high reliability. Bit error rate is low, and writing operation is also very simple and fast. But density is low, and also higher energy in terms of the PIM operation. Why? Because bit by bit, you need to iterate the operation, so energy efficiency is also low. On the other hand, multi-level cell case, you pack more information within one single cell. So in this case, 2-bit information, meaning that 4 different levels are represented, stored in the single level cell. Because of that, naturally, can you see here, noise margin is very, very narrow. So yeah, sometimes because of the non-ideality, some overlapped regime exists. So because of that, reliability is pretty low, but much faster and energy efficient. Why? Because multi-bits can be processed at the same time during the PIM operation. So simply saying that efficiency-wise, MLC is better, and then accuracy-wise, SLC is better, right? So these are necessary backgrounds. So earlier, regarding the PIM-related the transformer works, let me summarize. This is the analog PIM-based works. Number 1, Asadi HPC 2024. So they employed the mixed RRAM structure, analog PIM and digital PIM. But the problem is they relied on only single level cell, so that limiting the efficiency dramatically. Another approach is the sprint. Actually, this is from our own group's publication, Micro 2022. What we did was here inside, even before read the data from the memory, we know which data is important or not. So which token, which word is keyword, which word is a garbage. So we know that. And then only very important 25% of the important tokens are read and then delivered to the digital processor. So it was like the main idea. But as you can see, the role of the analog RRAM is only limited for the transformers, the token pruning task. And also anyway, even for 25%, we need to go through the expensive digital processor. So these are some limitations. So in consideration of all of those limitations, we propose a hybrid RRAM PIM architecture, so-called high flex PIM. If you take a look at transformer, we have 2 different types of the linear operations. First one is static. Static meaning that the weights are, after training, the weights never be updated. Those are frozen. On the other hand, dynamic, query key value, those are being updated runtime. So those are changing across the time. So for the dynamic linear operations, we employ simple single level cell digital PIM operation. Why? Mainly because to leverage very fast and cheap writing operation. Earlier, I commented that multi-level cell writing is very, very slow, very painful. Verify read operation, multiple writing operation. So instead of that, mainly because simple writing operation, we employ the digital SLC PIM for dynamic. Now, for the static part, ideally, we want to use MLC for all of the cases for higher efficiency. However, the problem in practice, This is any type of the task. There is an error tolerant part, error vulnerable part. So typically, error tolerant part, we enjoy efficient analog MLC operation. On the other hand, error vulnerable part, we use very, very accurate digital or single level cell operation. This is the common practice of this community. However, this has some limitation. Number one, error tolerant fraction is not that much limited. Number two, there is the demarcation, the separation, this boundary is very blurred. So from which domain we can cut here, here, or here, very, very ambiguous. So far in our community, we relied on inherent error resiliency of the model itself. But I would say that is the not ultimate solution. So we propose a little bit more proactive solution, meaning that we transform AI model itself to be more favorable form for analog PIM operation by using gradient redistribution. So as you can see, error tolerant fraction will be magnified so that we can enjoy efficient analog MLC operation as much as possible. On the other hand, we can also make a clear demarcation between error tolerant and also vulnerable part. So this is our two main goal of this project. Again, let us zoom in the transformer data flow, including self-attention, feed-forward, and also nonlinear operation like a softmax. So first of all, this is just time order, processing order. Token generation, QKV, is static-based one. FFN layers are also static weight matrix. On the other hand, QKV should be runtime generated, so dynamical matrix operation. So dynamic part, as I commented earlier, we are using SLC digital. On the other hand, the static weight, if we zoom in, we want to leverage MLC as much as possible, but only for the key part. To maintain accuracy, we are going to apply single level cell. But now there is a key problem. How do we distinguish critical versus non-critical or tolerant and vulnerable part? So to do so, we borrow the notion of the singular vector decomposition method from your freshman linear algebra class. Any type of the weight matrix can be decomposed into three matrices, U, sigma, V, and this is diagonal. This is the important, very big value. This is the small value, important and less important. And also column-wise, important, less important, row-wise, important, less important. So we are going to borrow this notion. So let us check the gradient. Gradient is what? Gradient is when you change the weight as a unit amount, how much accuracy will be impacted. This is the gradient. So gradient, we can say that this is the importance measure and also sensitivity measure. So as you can see here, before SVD, do you think that we can demarcate which one is important or not important? It is very, very difficult. Now let's see, after SVD, you can see that a little bit better. For the important rank part, we can see a little bit trend that it is actually getting more important. But still, I would say this is not sufficient. This is not satisfactory yet. So our ideal goal is to make a distribution to be like that. So that extreme small fraction, we are going to protect based on single level cell, but most of the 80 or 90% we can enjoy MLC. This is our ultimate goal. So let me summarize our recipe. So we, first of all, the equation is sophisticated, but key idea is we truncate the unimportant fraction. So we maintain original size of the matrix. And then if we truncate, we lose the information. Because of that, accuracy is impacted a lot. Accuracy is degraded. So usually we need to do fine tuning, meaning that training, maybe 2 or 3 epochs, a little bit trained, then accuracy is recovered. And then finally, we combine this guy pre-compute so that we can even compress the data even further. But actually during this process, so this kind of the fine-tuning has another very important role on top of the recovery of the accuracy, which is gradient redistribution. Let us think about you lost the information because of the truncation. And then now you fine-tune, then during the fine-tuning process, the loss of the information tends to be recovered by these survivors. And then especially the lost information tends to be recovered by this key part. Why? Because those are principal component. So this lost information tends to be more recovered by these important guys, but less recovered by these guys. So in terms of the figure, this is SVD without fine-tuning, and this is SVD after fine-tuning. So this important principal component tend to recover more because that is more important principal component. But so because of that, important guys becomes even more important. Less important guys going to be relatively less important. So because of that, we can utilize the efficient MLC for this less sensitive regime, but this part we can protect with the SLC. Yeah. And then now your natural question might be, okay, algorithm-wise it is fine, but hardware-wise, how do we assign number of the SLC? Meaning that, let us say you have the 100 banks, but out of the 100, how many banks you are going to assign for SLC bank and MLC bank? Because that ratio might change across the algorithm, data set, and also the model itself. So if we fix the number, the ratio, then we cannot reuse later for the other application. So simple answer is all of the banks are reconfigurable between MLC and SLC. As shown here, this is the MSB and this is the LSB. Then after ADC, we can simply shift to represent the bit position. On the other hand, the MLC case, let us say this is the 2-bit MSB, this is 2-bit LSB. In that case, we can simply shift by 2. So even in MLC case, by massaging the amount of the shifting operation, we can reuse SLC hardware for the MLC as well. So simply saying all of the arrays are the same, but we simply reconfigure amount of the shifting operation. And this is the high-level architecture, connected many processing unit through the global bus. And each processing unit, we have multiple of the analog PIM and digital PIM. And inside analog PIM, yeah, this is the same as I explained, including ADC as well. On the other hand, digital PIM, we don't have ADC, but we have special function unit for non-linear operations. Then for the test, we used the BERT, GPT, Llama, Vision Transformer, and Glue dataset, Wiki dataset. And for the Vision Transformer, we used the Cypher 10. And int8 format for all of the layers, QKV and linear, and also floating point 16 for non-linear operation. And we also compared with the state-of-art Asadi and Sprint and our own near memory processing baseline, and also non-PIM 2D systolic-based NPU as well. And then SFU was actually synthesized. And then now we analyze the accuracy by sweeping the proportion of the SLC amount. So if you zoom in, as you can see, if we don't have SLC at all, accuracy is degraded. But if you have increased the SLC, as you can see, accuracy is recovered. So for the BERT case, usually most of the cases with 5% SLC, we can recover most of the accuracy. But GPT-2 or Llama 3, we could achieve accuracy with a 5 or 20% SLC. Vision Transformer only 5% was sufficient to recover most of the accuracy. And also, even though we borrowed the notion of SVD and rank, and also even though we fine-tuned, at the end of the fine-tune, finally, the choice of the important vector to protect in SLC. Rather than strictly following the rank order, we followed the gradient-based method, so that it was actually slightly better than strictly following the rank-based one. So even though we borrowed the SVD and rank, But at the end of the day, final choice was based on gradient. Maybe that is because gradient is the measure to be connected to the accuracy more directly. And we could achieve the 1.6 or 4 times energy efficiency compared to, for the BERT and GPT-2 compared to ASADI. Why? ASADI is only using single level cell. And also we achieved near 5 times better energy efficiency than Sprint. Why? Because Sprint only used the analog PIM for token pruning case. On the other hand, the speed up, for the similar reason, we also achieved the near 2 times or 10 to 46 times energy speed up compared to the ASADI and Sprint as well. So let me conclude. Hybrid PIM exploited the digital and analog RRAM PIM. Inside analog again, we used the SLC-MLC. And we want to use MLC as much as possible. So gradient distribution reshape the weight importance to have dominant, meaning that 70 to 95% case can be applicable to MLC domain. And then compared to the SOTA, we could achieve at least 1.6 or 1.8 energy and speed benefit. Okay, so yeah, so these are references and then acknowledgement, and these are some prototype chips fabricated from our research group. Yeah, thank you so much for your attention, and then any question will be welcomed. Thank you.
Subscribe the channel to get the instant updates on our webinars.